voice of thanks to the organizer of this roaring conference. Just in case I hadn't got a chance to do my rant against no quantons in quantum fields, I put a few slides aside for that purpose here, but of course I got my chance to do my rant, so we can skip right through those. And I'll go to this point, which I want to make, which will be my departure. So far, all the discussion about the relationship of quantons to quantum fields has been in terms of stable quantons. But there are far more unstable than stable quantons. There are far more excited states than ground states. Excited states decay. There are far more radioactive nuclides than stable nuclides. And of subnuclear quantons, only the photon, the electron, the neutrinos, and their antiquantons are presently regarded as stable. We haven't seen the proton decay yet. The theory seems to demand it. However, if you go to the literature on unstable quantons, you find that among those pieces in the literature which are not just doing fast and dirty calculations for the purpose of comparison with experiment, the treatment of unstable quantons is characterized by persistent heterodoxy from mid-20th century on. It's a situation, you know, we have this situation in quantum mechanics and quantum field theory where you can teach any physicist the calculational rules in quantum mechanics and quantum field theory, and we all learn how to do the calculations for comparison with experiment, and except for a few subtle instances, we don't disagree on how that's to be done, and if there's disagreement, it only lasts for a short while and matters resolved. It's the question of interpreting what the processes all mean that leads to long-standing disagreement. And similarly, in the case of the literature concerning unstable quanton decay, it is those issues concerning what it all means that leads to disagreement in the literature. Here are two examples of issues on which people disagree. Exponential decay, is that a good approximation to the time dependence of metastable quantons as they decay? Or is it something fundamental, essentially belonging to the nature of an unstable quanton, and the deviations from exponential decay being a consequence of some corrupting influence sneaking in that doesn't really have to do with the unstable quanton? There is disagreement concerning this. How should we try to represent unstable quantons vis-a-vis group theory? If we decide to use unitary group representations, we're forced to employ reducible representations about the continuous spread in the rest mass spectrum of the unstable quanton. And as a consequence, there are some researchers who argue that we should not settle for unitary group theory representations, but we should go to non-unitary representations, which can be irreducible if appropriately chosen. And some would also prefer to not go with group representations, but with semi-group representations, as a consequence of not regarding the formation of an unstable quanton from what may be called its formation progenitors as being on the same level as the decay of the unstable quanton, its decay products. Should we allow unstable quantons access to pure state representation, or should we restrict them to mixed state representation? There's disagreement in the literature on this matter. This is especially strident disagreement when it comes to dealing with hadronic resonances, those strongly interacting resonances that decay so rapidly that we have, for all practical purposes, no chance of witnessing the time dependence of the decay process in the laboratory. Basis states. In the case of a stable quanton, the momentum eigenstates are the same as the velocity eigenstates. In the case of unstable quantons, they are very different. And the velocity eigenstates have the property of being transformable into one another under Lorentz boosts. The momentum eigenstates, three momentum eigenstates, mind you, I'm talking about. There are no such things as four momentum eigenstates for unstable quantons. The three momentum eigenstates do not transform into one another under Lorentz boosts for unstable quantons. As a consequence, some researchers much prefer use of velocity eigenstate basis, but not all. And you will see one reason of very recent vintage, if I make it to that part of my talk, why some people would object to the velocity eigenstate basis. What is the relationship of unstable quantons to the analytic structure of scattering amplitudes? The most traditional view is that associated with every unstable quanton is a pole on an unphysical sheet of the analytically continued S matrix. But as a consequence of analysis of the models and the data carried out by Gherardi and company, that's the same Gherardi of GRW, spontaneous state reduction, but done quite some time ago. It's not at all clear that this association of unstable quantons with poles on unphysical sheets has to be maintained. So there's disagreement about that. Should we assign to unstable quantons sharp spin? We are not permitted to assign to unstable quantons sharp mass because of their spontaneous decay and essentially the energy-time uncertainty relationship. But it's also the case that the assignment of spins to unstable quantons is intrinsically more delicate and vague than is the assignment of spins to stable quantons. And a few people, myself included, have proposed the notion that unstable quantons should be allowed indeterminate spin spectra, and that there are ways of experimentally attempting to discern this, but that's not the subject matter by any means. What's the relationship of unstable quantons to quantum fields? Unlike the case of stable quantons, the quantum fields associated with unstable quantons, if there's to be anything like a one-to-one association, cannot asymptotically evolve into free fields, as is the traditional view for the fields associated with stable quantons, simply because the unstable quantons disappear. They don't asymptotically evolve into non-interacting unstable quantons. They asymptotically evolve into their decay products. And finally, something more recent, which goes back to this question about momentum versus velocity eigenstate basis as the preferred way to analyze what's going on. There have been recent, by recent I mean within the last few years, discussions of Einstein dilation of lifetime versus non-Einstein dilation of lifetime, by which I mean deviation from rigorous classical Einstein dilation of lifetime. In fact, a recent calculation has shown by Shirokov that if you use the velocity eigenstate basis, the lifetime for a non-zero velocity state is contracted rather than dilated from the lifetime of a zero velocity eigenstate. Now, something is obviously wacky there, but the derivation is very clear and straightforward. It turns out that there's no agreed exact theory of unstable quanton structure and interactions to which the contributions in the literature are approximations or can be regarded as approximations. Yes?
Can I just ask one clarification? What do you mean by unstable? I mean, there's a lot of...
They decay spontaneously. That's all I mean.
That's all you mean?
Yeah. So, in the rest of my talk, in order to show you some of the considerations that can come up, I'm going to adopt assumptions of my own. I don't regard these assumptions as written in stone. They are for the purposes of simply developing some ideas and to work with. They are assumptions that I am presently inclined to embrace, but as I say, I don't regard them as the way the field should go if we were only wise enough to see so. I allow pure state representation of unstable quantons in a very conventional Hilbert state space. I'm going to assume that any unstable quanton can exist in a state that I call an instantaneous single parent state, or ISP state, in which there is some definite time at which the unstable quanton is the only thing existing, except of course for the field theory vacuum. There are no other quantons around, stable or otherwise, at some time. unstable quantons have access to such states. And that after the no decay time, as I will call it, you have some probability of finding decay products and a probability less than 1 of finding the parent still surviving. I will assume the Euclidean and superposition invariance of these ISP states and the no decay time. In other words, if I submit an ISP state with a definite no decay time to a spatial translation or a spatial rotation, it remains an ISP state with the same no decay time. If I superimpose a bunch of such states, all of which have the same no decay time, the superposition is an ISP state with the same no decay time. I'll adopt a definition of lifetime that's independent of the question of whether exponential decay is fundamental or an approximation. So we won't talk about lifetime in terms of exponential decay, except in a very passive way.
Sorry, did you say what no decay time was?
No decay time is that instant in time at which the parent quanton is the only thing existing. No decay products can be found.
It's not a duration.
No, it's not a duration. It's an instant. And I'm going to assume covariance under the inhomogeneous Lorentz group. Now, assuming covariance under the inhomogeneous Lorentz group means that I'm going to have to talk about states that are quite different from these ISP states, as well as the ISP states. But it is by admitting the existence of the ISP states that I'm forced by this covariance assumption to a much larger class of states. With those assumptions, I will examine, and when I say I will examine, this is done in the paper upon which this talk is based, whether I will get to talk about all these issues in this talk. We'll look at the unitary evolution of ISP momentum eigenstates. There's a reason for focusing on momentum eigenstates. Their interpretation is somewhat clearer than finite norm states, especially for the purposes of a talk like this. We'll look at the behavior under boosts of ISP states, in which case ISP states lose their ISP status and become a more general class of states, which I just call SP states, single parent states, but not instantaneous single parent states. The examination of the relationship of unstable quantons to quantum fields will be first looked at in the form of the vacuum SP state matrix elements of fields. So we take a field and put on either side of it a vacuum state to the left, let's say, and a single parent state to the right, and examine such matrix elements. I will look at the relationship between the velocity eigenstates and deviation from Einstein dilation of lifetime. At least I hope I can do that. Probably I won't be able to say much about two-point vacuum expectation values in quantum field theory involving unstable quantons, but all of these topics are discussed in my paper. Starting out with a pure state representation in conventional state space and the existence of instantaneous single parent ISP states. I'll use the Heisenberg picture throughout, in which case a symbol like this psi comma t describes an entire unitary history of an isolated system, which at the time t, which I call the no decay time, consists of just one unstable parent quanton. At all other times, the probability of finding the parent quanton undecayed is less than 1, and the probability of finding decay products, these may be what I call the decay products after the no decay time, and formation progenitors before the no decay time, but we talk about the same kinds of things. The probability of finding decay products is greater than 1. And the relationship between
Greater than 0.
I'm sorry, greater than 0, yes. And the relationship between a Heisenberg picture state with the no decay time t, let's see this with the pointer here, with the no decay time t and the no decay time 0, is just given by the standard unitary operator representing time translation. There's actually t there, it's squeezed so tightly up against the h that you can barely see it. Euclidean and superposition invariance of ISP no decay time. By combining the translation and superposition, we can build, of course, three momentum eigenstates out of any finite norm state given. What I'm talking about now is extremely elementary stuff from elementary quantum mechanics, and you might be a little puzzled that I'm bothering to dwell on it. But the point is that I'm here dealing with some features of the treatment of single unstable quanton states that are the same as dealing with single stable quanton states, and I want to emphasize that similarity for my present purposes, so that when I go on later to talk about ways in which the unstable quanton states differ from the stable quanton states, we can see that difference vividly. So here's some of the technicalia. I take this superposition of translated states multiplied by appropriate phase factors, and I get this construction here, and I have the delta function which projects out the momentum eigenstate. Sorry about the possibility of a little culture shock here. Unlike other speakers at this conference, when I write down a delta function, I will not then immediately jump to something like a bioalgebra states. Delta functions speak to my heart of hearts, and I think they're wonderful. I always use them whenever the opportunity arises. And here's the inverse, where we reconstruct the norm states from which we began by a linear superposition of the three momentum eigenstates. Definition of the lifetime independent of exponential decay. One does have to talk about the survival amplitude. Here we have the two ISP three momentum eigenstates with no decay times t prime and t, different no decay times and different three momenta. And because they are both eigenstates of three momenta, and the three momenta is conserved, we have this delta function of the three momenta, and the dependence on the time difference is just given by the survival amplitude. The survival probability is then the absolute value squared, and the lifetime will be defined this way. Good Lord, what does that ampersand do in there? That ampersand is supposed to be a dot on top of the p, a time derivative. It didn't look like that on my computer, but I use a Mac, and I think that could be sort of some discrepancy. So anyhow, that's supposed to be the negative time derivative of the survival probability sitting right there. And the reason you put it in that way is that what you're doing is you're averaging the time of decay weighted by the rate of decay at the time in question. And then by a little integration by parts, making use of the fact that the survival probability vanishes at t equals infinity and is unity at t equals 0, that enables you to throw the integral into this form. So that will be our definition of lifetime. And it turns out, to whatever degree the survival probability is dominated by this kind of exponential form, to a corresponding degree, the defined lifetime ends up being tau. So this is compatible with the traditional view of life. Unitary evolution of these momentum eigenstates. If we start out with a momentum eigenstate with a no decay times 0, and we relate it to a momentum eigenstate with no decay time t by this time translator which pulls back the t to 0, then I can expand this expression in terms of the momentum eigenstate with no decay time t and a coefficient which is just the expectation value of the unitary operator, and is also the survival amplitude. And then when we construct this first term that way, this term is guaranteed to be orthogonal to the first term and to have the same kind of normalization as does the first term, the proportion to the delta. However, whereas this is an ISP state, which at the time t consists of just one unstable quanton, this is no such thing. This is a state of definite free momentum k, but at the time t it consists of nothing but decay products. So this decomposition provides a clean decomposition from a state with the parent at the time t and the state with nothing but decay products at the time t. We started out with nothing but the parent at time 0. By the time t, some of the parents, well, one of the parents, there's only one parent, but the likelihood of the parent surviving has dropped by the modulus squared, this, and the likelihood of the decay products has risen. How do I know that this consists only of decay products? It's a consequence of the fact that this orthogonality relationship holds for any k and k prime, because what that means is that this momentum eigenstate is orthogonal not only to ISP states of the same momentum, but to ISP states with the no decay time t of any momentum, and therefore to the entire ISP state space with the no decay time t, so it can only consist of decay products. That's that possibility. Boosts. On applying a boost, both the symbols psi comma t for ISP states with no decay time t that have finite norm, and k semicolon t, I don't know why I switched from comma to semicolon, but k semicolon t for no decay for ISP's momentum eigenstates, 3 momentum eigenstates with no decay time t. They lose their ISP status. They no longer have any no decay time, and furthermore, kt loses its 3 momentum eigenstate status. That's what happens under boost. Now maybe that's immediately obvious to you. That would be wonderful. But usually it isn't, right? So let's look at the space-time diagram. Here's a space-time diagram in which the no decay time, now called t0, is represented by this horizontal bold-faced bar. And here's the what was originally the 3 momentum, the sharp 3 momentum of the state, but now represented as the 4 momentum, the 0 time complement. And here, for purposes of later comparison, is a time-like vector pointing from the origin of coordinates to the no decay time, which of course is a no decay hyperplane. This is an instantaneous space-like hyperplane. Now we could consider a passive boost in which we transform not the physical state of the system, but the perspective of the reference frame from which we are assessing things. So we look at things from the perspective of the prime frame of reference, and obviously in that frame of reference, this no decay time is no longer a no decay time. But it's still the space-time slice on which the system has probability unity of just being an undecayed, unstable parent. So we will refer to it as the no decay hyperplane. The corresponding active boost stays with the unprimed coordinate system and transforms the physical state of the original ISP state. It's now a single parent state, no longer an instantaneous single parent state. It has a no decay hyperplane that is not a no decay time. And the P here and the eta tau are the transfer of the 0k and the 1, 0 CT0 from the previous slide. And here is a lot of the transformation equations. And oh, sigh. Okay, what I want to focus on for the moment is this. This is the equation, sadly scrunched, that takes the place of the 3 momentum eigenvector eigenvalue equation when we were back with the original state, which was an ISP state with no decay time. What is sitting here is the total 4 momentum minus the time-like unit vector eta mu times the inner product of eta and the 4 momentum, acting on the actively boosted state now characterized by P eta tau, and it has this eigenvalue. So the eigenvalue P, which will appear again and again, it's a 4 vector to be sure, but it's a space-like 4 vector. It's not a time-like 4 vector, because it's orthogonal to eta. It's an eigenvalue of this complex, which is orthogonal to eta. Eta is time-like. So space-like. And this is just some technicality that we don't have to dwell on. The corresponding normalization, orthonormalization of the momentum eigenstates, the corresponding expansion of finite norm states in terms of the momentum eigenstates, but now with no decay hyperplanes rather than no decay times. And this Lorentz invariant delta function that is appropriate for dealing with these non-instantaneous. Technicality, I'm just going to skip right through that. Okay, let's talk a little bit about the relationship of these SP states, single parent states, on non-instantaneous, in general, non-instantaneous hyperplanes. Oh, heavens. This is the Dilation. That should be a square. Right? Okay, what looks like Quanton. What's a squanton? Anybody guess? Guess. What's a squanton? Stable quanton. Exactly so. The vacuum squanton matrix element of the field. For any field phi of x, and I emphasize that what I'm going to say about fields on this transparency and the next applies to a field of any tensorial spinorial rank whatsoever. I just write it down as a scalar field because I don't want to write down all the indices. But what I say about it applies to any tensorial spinorial field whatsoever. Okay, we have any field, and we have any, oh crap, sorry. Any single stable quanton state psi. So I don't have any reference to a time here or a hyperplane. This is now a stable quanton state. It's not decaying. It's all by itself. It's just going to sit there. So it satisfies this eigenvector eigenvalue equation for the total form momentum squared. The eigenvalue is just proportional to the square root of rest mass, which is sharp. So we use the Heisenberg equations of motion and this eigenvector eigenvalue equation to obtain this Klein-Gordon equation. That's what this is supposed to be, the Klein-Gordon equation, for the matrix element of the field between the vacuum and the single stable quanton state. This is not only independent of the tensorial spinorial rank of the field, this is independent of whether there are interactions present and of their nature. It makes no difference. The field itself will not satisfy if there are interactions present. The field itself will not satisfy this equation, but this particular matrix element of the field will, regardless of interactions, regardless of the kinematical structure of the field. So the Klein-Gordon equation holds for all vacuum quanton matrix elements of any field, regardless of interactions. Now suppose we go to the vacuum U-quanton, or unstable quanton matrix element of fields. And what replaces that eigenvector eigenvalue equation with the definite mass for stable quantons is this equation. And by the way, let me say that both, if you remember, we talked, is there an eraser here? A few slides back, we were talking about a unitary evolution equation, and I said that the two terms were orthogonal, and the second term contained only decay products at the no decay time t, and the first term contained only the unstable parent with no decay time t, so on and so forth. That equation was an equation similar in structure to this one, and all these equations are of the following form. Some operator on some state gives rise to the same state times the expectation value of the operator plus another state that is determined by the operator acting on the first state times the RMS deviation of the operator in that state. And it always turns out that the norm of this psi sub A is the same as the norm of the original psi, and that psi and psi sub A are orthogonal. I'm using that feature of operators on states in several instances. I used it for the unitary evolution equation, and I'm using it here where the operator is the square of the total form momentum. Here's the expectation value, the same state is operated on. Here's the RMS deviation of the full momentum square, and here's the state that's orthogonal to the states. In this case, if we use the Heisenberg equations of motion for the field, whatever the field is, we get this inhomogeneous Klein-Gordon equation satisfied for the field's matrix element between the vacuum state and the SP state. Over here we have the vacuum state and not an SP state, a state that's orthogonal to the SP state. But we always get this equation. It doesn't matter There may be other equations also satisfied. Suppose this was a Dirac field, and I put the Dirac operator here instead of the Klein-Gordon operator. I get something else on the right-hand side. Well, there's always, since it's an unstable quanton, we're guaranteed there are interactions present, because it's going to decay. So there are at least those interactions present. But whether it's a Dirac field that enables me to derive another equation, this inhomogeneous Klein-Gordon equation always is satisfied. And if I go to the particular case of the momentum eigenstates with the no decay hyperplanes, then it turns out that here I have a state that consists solely of the parent on the eta tau hyperplane. That's the same as up here. But here I have a state that consists of nothing but decay products on the eta tau hyperplane, and that's not true up here. For the finite norm case, this state will in general be a mix, or a superposition, I should say, of both the undecayed parent and the decay products on the eta tau hyperplane. When you go to the momentum eigenstates, it's a clean separation. This is just to emphasize what I just said. The polynomial for time. Let's pass on.
Sorry, more like
So now let's talk about velocity eigenstates and lifetime contraction. For these SP momentum eigenstates, we have, as we saw before, and this time the equation doesn't seem quite so scrunched together as before. This part of the total four momentum operator that's orthogonal to eta, and eta is the time-like unit vector that's orthogonal to the no decay hyperplane. And here's the eigenvalue for that operator. Suppose that it's chosen to be zero. Suppose we look at the particular case in which the momentum eigenvalue is zero. That's all four components of the momentum eigenvalue are zero. Then the original equation can be thrown into this form by just taking this term on the right side. And from that, you can convert it into this equation, which is a velocity. Okay, this is supposed to be a little horizontal arrow telling me that in the numerator I have the space components of the four vector eta. Okay. These are the space components of the total four momentum, what we would otherwise call the total three momentum. Here's the time component. We've constructed this ratio successfully converting it into an eigenvector equation for that ratio, simply because all four components of the total four momentum here are proportional to the same operator acting on the stated question, multiplied by this C number for vector. And so we have built ourselves a velocity eigenvector. This is a velocity eigenstate. And while going backwards is a little trickier than moving in the direction I've come from here through that to this, you can go backwards. That is to say, if you start with any vector, it doesn't have to be a vector that's declared explicitly to have to be an SP state with a no decay hyperplane eta tau. Doesn't matter. Just call it the U vector. From this statement, you can work your way back to a statement like this. The velocity eigenstate basis champions interpret all velocity eigenstates as having no decay times. Now, I don't mean by that when they work with velocity eigenstates, they say, this is a state in which the unstable parent has a definite no decay time. They never say that. But they manipulate these velocity eigenvectors in such a way as to strongly suggest that they must believe that, because nothing else would motivate the manipulations they undertake. In fact, I'm in the process of putting together a no-go theorem, which I'm going to try to make just as very rigorous as I possibly can. A no-go theorem to the effect that velocity eigenstates with non-zero velocity eigenvalues can never be interpreted as describing unstable quantons with definite no decay times. They must always be interpreted as they are interpreted here, as single parent states with no decay hyperplanes that are non-instantaneous. And as soon as you have a non-zero U is just just this ratio, and therefore that means that the spatial components of eta are non-zero, and that means that the no-decay hyperplane is non-instantaneous. However, let's forget all that. Let's assume, as workers employing velocity eigenstates do, that it's just a velocity eigenstate. We'll just label it by the u. And this turns out to be the Lorentz invariant normalization for such velocity eigenvectors. And then there is a derivation by Shirokov, and it's been streamlined by Hegerfeld, and it's the same Hegerfeld of superluminal evolution thing, to the effect that if we calculate this quantity, which here's the normalization, the invariant normalization on the velocities, which are conserved, even though they're not free momenta, they are free velocities, and they are conserved for single parent unstable quantons. And here's the invariant normalization. And here is the factor that describes the survival amplitude. Right? And clearly, this is being treated as a state which has a no decay time, because what you're asking is, okay, we start out with a state, say time equals 0, and we ask what has happened to it by the time t. And this is the survival amplitude. It's supposed to tell us that. What you get is this, and this is lifetime contraction. And it's unequivocal, but I would not be surprised if you find it hard to believe. Therefore, there's the equations. You work your way through those equations, you can't escape it, you get lifetime contraction. So what in the world is going on? Well, my argument is, well, you couldn't, actually, you couldn't work your way through these equations. I have them on the paper, it's some way to read them. All right, let's assume that I'm right, and that a velocity eigenvector with non-zero velocity is actually a state in which the unstable quanton does not have a no decay time, but has an appropriately non-instantaneous no decay hyperplane. And this will be it. And then we compare that hyperplane to what I'm going to call the lifetime hyperplane. This would be the hypothetical hyperplane on which all the decays would occur if they all occurred at the lifetime after the original preparation of the unstable quanton on its no decay hyperplane. So that, I'll call that the lifetime hyperplane. It's simply separated from the no decay hyperplane in the time-like direction normal to the hyperplanes by the amount of the lifetime. And notice that this interval, this time-like interval from 0 to b, is the time interval between those two hyperplanes in the frame of reference in which this unstable quanton has the non-zero velocity u. And that time interval 0b is this time interval. It's contracted. It's less than this time-like interval in magnitude. You might want to say, well, why do you look at that time interval? Sure, that gives the same contraction that Shirokov-Hegerfeld derived, but what's the significance of that? Why shouldn't you look at OC? OC from here, this is the time interval between these corresponding space-time points, 0 and A. And that time interval is admittedly the appropriately dilated time interval. But there's no corresponding point here, because these unstable quantons are not localized. We're talking about velocity eigenstates. They are on the they are initially on, it is on, I should say not they are, but it is on the hyperplane entire. And the only question that one can ask that has observational content for such a velocity eigenstate is, what is the time interval separating the hyperplanes? The no decay hyperplane from the lifetime hyperplane. And that time interval is what Shirokov and Hegerfeld found. And it's exactly the appropriately contracted time interval. Let me continue a little bit longer on this. Suppose we go from velocity eigenstates. By the way, this result convinced Shirokov that velocity eigenstates, there was something wrong with them, and you shouldn't use them. And after obtaining this result, he went to momentum eigenstates. It's not clear to me that Hegerfeld was so willing to just throw the matter aside, that Hegerfeld felt, gee, this is really weird. But now, let's put them aside at least for the time being and go to the momentum eigenstates. This is the integral representation for the non-decay for the survival amplitude, survival amplitude with a momentum eigenvalue p. It's an integral over the mass spectral function of this exponential. Notice I have the square root here of u squared minus p squared. If you're bothered by the minus sign, p is a space-like 4 vector, and I'm using the plus minus 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 method, so that's why the minus sign is there. If you plug this expression into the definition of lifetime, it's first of all this, but then you do a little Fourier analysis, and it comes out to be this. Now you may recognize this factor as being essentially an Einstein dilation factor. But of course it's integrated over all the masses that contribute to the mass spectrum of the unstable quanton. So Einstein dilation, exact Einstein dilation of the lifetime, which would be something like this, in which there was a single Einstein dilation factor, is at best an approximation. Because you could expand this about a mu0, which is some kind of average mass in this mass spectral function, and you would get correction terms in the expansion. Furthermore, since this lifetime depends on the momentum eigenvalue only through this invariant square of the 4 momentum, that means that if you boost the state, you don't change the value of this lifetime at all. The p dependence has to do with accelerations, not boosts. The accelerations are genuine changes in the square of p, and boosts will not produce those genuine changes. That raises what I think would be an interesting question. What is the Unruh effect on unstable parent quantons? And now what I mean by the Unruh effect is not just transforming to a boosted frame, but genuinely accelerating, changing the momentum eigenvalue of the unstable quantum. Here's an example diagram, a space-time diagram example of how the lifetime varies with momentum eigenvalue. Here's a hyperplane. Here's a lifetime hyperplane if the momentum eigenvalue is p1. It's a larger momentum eigenvalue than the lifetime hyperplane is further away. So on and so forth. What's the time?
You've got a minute.
A minute. Okay. The thing that I won't talk about in any length at all, but the next point is going to be field theories, 2-point vacuum expectation values. For field theories, what we do is we start with this vacuum expectation value of a product of fields at distinct space-time points, and then consider the following. Insert in here a complete set of decay product states, and compare that with inserting between the fields a complete set of single-parent unstable quanton states of the kind that I've been talking about. Now this is going to be hyperplane dependent because of the dependence of those states on things like eta and tau. This is not going to be hyperplane dependent because I'm thinking of a simple model in which all the decay products are stable quantons. But to my amazement, it turned out that these things essentially matched exactly, except for the tiny little replacement of one factor of the square root of q squared, where q is the total 4 momentum of the whole set of decay products. One little factor square root of q squared replaced by eta dot q, where eta is the orientation of the no decay hyperplane of the unstable quantons. And this turned into this. Now I don't know exactly what the significance of that is yet, but it's tempting to a person like me who sees hyperplane dependence everywhere to think that the possible replacement of local fields by hyperplane-dependent fields may in fact justify this transition. In any case, it seems to me that in this field there are many aspects and approaches. Well, first of all, there are many aspects and approaches that I haven't touched on here in the literature concerning unstable quantons. And I think there's much interesting work to be done, not just by physicists, but to some degree also by philosophers of physics, because there are clearly questions of just interpretation of what's going on in these matters, and not, I don't think all of these questions are questions that can be resolved perfectly by resort to this term. Okay, thank you. one consequence of that is not only a volume matter, which is the other reason why I speak so loudly, but also the speed of speech. So, because when people talk fast, it comes through to me like a burst from a Uzi submachine gun, and I just don't hear what the question is. So, a paced delivery, at least. Yes?
Okay, I mean, a couple of questions. First one, is there an issue whereby in your formulation we're assuming that there is some definite time at which I can say there's an unstable quanton present? Now, I think about the kind of way in which, say, a radioactive particle might come into being. Say I take 2 protons, or 2 electrons, say, and slam them together. It feels as if the creation time as well is going to have a spread in that situation. I'm not sure that's particularly a problem. I'm just interested. I think you could just integrate over a spread of time or something.
Right. I think my position is that in a situation like that, for instance, suppose we consider the formation of a rho meson, which is a hadronic resonance, by having 2 pions come together and form the rho meson. And then the subsequent decay of the rho meson, which goes in roughly 10 to the minus 20 seconds. That's something that happens so fast that if you're willing to grant rho mesons access to pure states, as I wanted to do, that for all practical purposes, 10 to the minus 23rd seconds is short enough to be able to introduce something like a no decay time. Although, again, you might say, well, the strong interactions really work rapidly and maybe at the appropriate level of time scale for the strong interactions. That's not a wise thing to do. Okay, I would probably have to concede on that. It would be a question, it would be an issue. I agree with you, it would be an issue. If you deal with metastable decay, weak decays, muons are unstable. They are formed in various ways, either by the decay of pions themselves, or, strictly speaking, according to theory, it's possible for a muon to be formed by having an electron antineutrino, and a muon neutrino come together. The probability of that would be extremely small. But muons live so long that we actually observe them. We observe their tracks in detector apparatus. And to deny to a muon something like a no decay time or a no decay hyperplane would seem to me to place considerable demands on the theorists to model what is going on if you don't want to admit that possibility. But, you know, if you push hard enough, yeah, sure, it can be an issue.
David?
I have said my first. And the second question is probably a bit quicker. So I was just trying to understand that boost independence of the decay time. Now check if I got this right, because my initial instinct was, hang on, we've got lots of evidence that says things that decay while moving quickly have time dilated decay times. But I take it what's going on there is unchanged hyperplane.
Yes, yes. But I'm glad you raised that, because I wanted to say something about that, which I skipped over. You might ask, we do have empirical data whereby, for all practical purposes, things like muons. The reason muons reach the surface of the Earth is because of time dilation. They're created in the upper atmosphere by decay of pions that come from cosmic rays. If they didn't suffer time dilation, they'd never make it to the surface of the Earth. They make it to the surface of the Earth only because they suffer time dilation. And measurements have been made as to what that time dilation is, and it's very, very close to the Einstein time dilation. Now, admittedly, when I talked about the time dilation of the momentum eigenstates, we got an approximation to Einstein time dilation, and you might say, well, that's probably going to be okay. But you can do better. And you do better by leaving momentum eigenstates, or rather superimposing them into partially localized states, partially spatially localized states. And as soon as you do that, my argument on some of the hyperplane diagrams that I had here, in which I said, no, there is no corresponding point from the no decay hyperplane to the lifetime hyperplane. The velocity eigenstate, or in another case, the momentum eigenstate, they're on the hyperplane entire. They're nowhere on the hyperplane. But as soon as you start to form partially localized states, then they are more or less somewhere on the hyperplane. And then there is at least loose localization between a certain region on the decay hyperplane and a corresponding region on the lifetime hyperplane. And as soon as you take that into account, you come closer to Einstein lifetime dilation, except it's still approximate, and then it's approximate for two reasons, not just one. Remember that the reason we had approximate Einstein dilation in the case of the momentum eigenstate was because of the spread of the mass. And the Einstein dilation factor was mass dependent, so you got only an approximate Einstein dilation. If you now superimpose momentum eigenstates, you're also going to have a spread in the Einstein dilation factor under the integrals due to the momentum spread as well as due to the mass spread.
Yes. First, just kind of a historical question. I'm forgetting right now how the details of this go, but I'm wondering if you look at the variant of scattering theory that was developed by Pollock and Noel in the late 1950s, because as I recall, unstable particles were one of their motivations for developing this particular formalism for scattering theory. The sorts of thoughts you had about how the stable states you have asymptotically.
But the asymptotic states could only consist of the decay products, right?
Exactly. So they're thinking, yeah. So they set up the limits differently.
Okay, right.
So that might be. I don't know if you looked at it or not.
But what I know, and I don't know the details of this very well at all at this stage of the game, but I know that there is still disagreement among the field theory workers as to how to set up the relationship between fields in the S matrix and between fields and the unstable quantons when they actually want to talk about not just the S matrix that comes from formation progenitors into decay products, but they want to restrict themselves to an S matrix that is first as the formation progenitors, and they form unstable quantons. And the unstable quantons then interact in an S matrix, and they come out of the S matrix, and then they decay. And apparently, there are metastable unstable quantons that live long enough, such as muons, such as neutrons, they live 15 minutes, in which we can really imagine that happening. But the problem of trying to theoretically set that up is a little delicate and a little touchy. So the point I'm trying to make is that there still seems to be disagreement within the literature concerning how most appropriate.
My other question was, I guess more of a question of clarification. I think I lost the thread somewhere. About, so I was wondering if you could just summarize again what you take to be the most interesting respects in which unstable quantons differ from the stable ones, which could be illuminating as to the nature of quantons.
It won't suffice for me to say, well, they decay. No, it won't. I would say, for me personally, the most interesting respect, but to some extent this is a consequence of the fact that I don't regard myself as having a very deep understanding as to how these issues should be resolved. I've just begun to work on it. But for me, what is most interesting is that because these unstable quantons must have, modulo David's first question, must have a definite no decay time. Some time, they must have access to states in which there's a definite no decay time. That also means that under Lorentz transformations, they must have access to definite no decay non-instantaneous hyperplanes. So I find that very intriguing, that this is, unlike my previous studies of hyperplane dependence, in which I hypothetically inserted hyperplane dependence either into discussions of localization, position operators, or discussions of state reduction. It seems to me that in this instance, the hyperplane dependence is forced upon me by an assumption that does not initially refer to hyperplane dependence at all. So I take that to be the most intriguing feature of all of this right now. Yes?
I think so my question really is to say what you said in response to David's second question, but in a sort of more boneheaded way. So maybe the answer is just to explain more what you mean by the sort of Einstein dilation. So let me just sort of set up how I'm understanding it now.
Okay.
So when you say that, I just think you're taking sort of classical, elementary special relativistic time dilation. So you've got a sort of time that's the lifetime for which are the ones that are decaying?
Say again?
Which are the mesons that are
Muons.
the muons, right? So
Muons.
right, so you've got a decay time for the muons in their rest frame. You just dilate it in the normal kind of way. Okay, that's what I'm understanding by the Einstein dilation.
Yes, that's correct.
So now I'm just really puzzled what corrections. I mean, that just seems to follow for
Because that rule you just mentioned, treats the mass of the muon as exact. Because if you could not treat the mass of the muon as exact, you wouldn't. No, let me check what I'm saying now. Yes.
So can I just say what's sort of,
Yeah.
okay, so what's now in the back of my mind is it seems there must be some kind of some kind of non-Minkowski element entering into the theory or something?
No, there is
be
not.
wrong or
Absolutely
something?
not.
So, okay.
No. The theory, as I presented it, is Lorentz covariant. Let's say this. If you do the calculation rigorously using velocity eigenvectors, which have this virtue of transforming into one another under Lorentz boost, you get the Shirokov result. You don't get the Einstein dilation result. I have suggested a way of interpreting that Shirokov result as not so unsensible when you realize that velocity eigenvectors refer to non-instantaneous decay. If you work with momentum eigenvectors, then you get approximate Einstein dilation because of the mass spectrum. Now, in the case of a metastable, unstable quantum like a muon, the mass spectrum, at least in the Bright-Wigner version of the mass spectrum, it has this exceedingly narrow peak. It's not exact. It's not a delta function peak. It's a resonance peak, but it's very narrow resonance peak. And so when we do the classical calculations of lifetime dilation, we ignore the width of those peaks. We ignore them completely. We use it as if it were an exact mass, an exact rest mass. If it were exact, then the momentum eigenstates would be the same as the velocity eigenstates. So the point is that if you do the calculation in a rigorously quantum mechanical way, you either get the lifetime contraction from the exact velocity eigenstates, or you get the lifetime approximation, or the dilation approximation due to the mass spread using the momentum eigenstates. And you can come partially back towards something like the classical calculation if you work with states that are partially spatially localized, superimposing various momentum eigenstates. But there's no way you're ever going to get exactly the standard back-of-the-envelope dilation calculation, because that just ignores the spread of the mass spectrum.
So we do it, okay, so we do it one of the ways you've been sketching. So now we've got a time then, we should be able to transform back into sort of the rest frame of the muon, right? And get a better decay rest frame, decay time?
A better one.
Or one that takes into the spread of, spreads of masses into, I mean,
No,
I guess I'm still having a...
The choice of frame doesn't have anything to do with taking into consideration the spread of the mass. It's the way you do the calculation, whatever frame you're in. You either take into consideration the spread of the mass or you don't. If you use the formulas that I have on the screen, you automatically take into consideration.
Right, so I guess there's sort of like naive way of thinking about it, there's sort of two things go into the calculation. What you think the decay time is in the rest frame and Lorentz transformations. So you're saying we still have the Lorentz transformation, so it must be that there's something wrong with what we thought we put in as the decay time in the rest frame.
If by the rest frame you mean the frame in which P equals 0, what I was calling P, that can be a frame in which the velocity is anything. Because the velocity corresponds to p equals 0. If by the rest frame you mean u equals 0, which means that the 3 vector p equals 0 as well. That's the one case in which the velocity eigenstate and the momentum eigenstate. It's the one case in which the velocity eigenstate is an ISP state with a definite no decay time. I don't think I really understand your question, so I don't think I have a
Well, I mean, so again, so I guess I'll just say the same thing again, and then maybe there's something wrong about the way I'm thinking. So that when you're doing your undergraduate relativity course, you kind of do this calculation and somebody tells you the half-life for a muon,
right.
and then you say, oh, let's apply time dilation to it, and we get a longer time.
Yes.
So everything you're doing is Lorentz covariant, so it's like the problem can't be in the sort of transformation part of that story.
No,
it must be in
That's right.
the half-life side
And
of
the
that
way
story.
that, using my approach, the way you would try to reproduce the calculation you just suggested, the most simple-minded way, which may or may not get sufficient accuracy to satisfy you, is to forget about localizing the states and just do the approximate Einstein time dilation and see if the approximation is good enough to satisfy you. If it's not good enough to satisfy you, then also look at the result of localizing, partial localizing of the state, then do the calculation. Now there may be some instances in which partial localizing will improve the Einstein approximation, though if you localize too much, you'll ruin the Einstein localization, because you'll start to get the analog part of the expression is spreading from two tightly localized states. Now if it turns out that by using that neither of those schemes will improve on the quick and dirty classical calculation, then the quick and dirty classical calculation is just wrong. And presumably, in instances like that, it would not be supported by experimental data.
I think the time has come to call on the hardcode.
No.
Is there some significance to that?
One of the things that you have made a couple of times with quanton rant, but I want to, and at least to a naive observer, when you go to these more complex decaying quantons, it looks like you have even more grounds for challenging the appropriateness of thinking of these as something on particles. So not something like, but too much like.
I agree.
And I was wondering if you might want to sort of say how that could, just...
I can't say very much on that at this time. I agree completely with the spirit of your question. But at this stage of the game, I'm still at too superficial a level in digging into these issues to know of some really significant aspect of our unstable quantons that would fly even further in the face of the particle conceptual apparatus than is the case for stable quantons. But I agree completely with the question. Yes.
Yeah, I think one of the things that might work in that regard is to say, well, if you were talking about classical point particles, instability would mean that you weren't really dealing with a particle at all, you were dealing with the bound state of a few particles, right?
Why would
But
it mean that? Wait.
Sorry.
Why would it mean that?
Well, just, you would think that if it's possible for this system to eventually bust apart, that it must have have these parts.
Well, if that's what it does when it decays.
Right.
That's not the way we think of decaying of a muon.
Yeah, exactly. So with weak decays, for instance, it's not like you have a bound state that's breaking up. You
Right.
have a system that's
Right.
turning into
Yes.
parts that it didn't have before the decay.
Right.
So you might see that as something that wasn't there in the classical notion of particles.
Yes, I agree. That is something, I mean, you know, if you have just one, for instance, remember that Klein-Gordon equation I had for the quanton vacuum matrix element of any field whatsoever, regardless of the interactions that are present or their nature? Well, why do you get that Klein-Gordon equation? Well, because what does one quanton do if it's all by itself? It just sits there. It doesn't do anything. But as soon as you put an unstable quanton in that state, in place of a stable quanton, no matter what else is going on, it decays. So it does something, and new things are produced. So yes, I agree with, again, the spirit of that. But, you know, you could say a champion of retaining the particle conceptual apparatus in the quantum context would say, well, that's just one particle going into three particles. I mean, why can't I still talk about particles? But, you know, I will keep digging and see if I can find a deeper reason to refute that.
What happens if I evolve an unstable quantum backwards?
Well, people disagree. That's one of the reasons why there's disagreement as to whether to permit quantons access to pure states versus just mixed states. That's one of the reasons why people disagree on whether to represent the, what I'll call the algebraic structure of unstable quantum state spaces by unitary representations of groups versus non-unitary representations of semigroups. It's the creeping into the whole discussion of the possibility of genuine irreversibility. So there is real disagreement on that. I, at present, personally, am inclined to think that unstable quantum decay does not entail any genuine irreversibility. But it is also true that the decay of the neutral K-meson, which is the one instance we know of in which CP conservation is violated, therefore, vis-a-vis the CPT theorem, that means time reversal invariance is violated, that gives rise to question, does this really mean that this is an irreversible process? And some people have gone so far as to conjecture that the violation of time reversal invariance in neutral K-meson decay is the ultimate source of the second law of thermodynamics. Now, in my opinion, that is really going out on a limb.